but we'll find out. Okay, so today we are going to do a little bit of review and tack on a little bit of new stuff from pre-calculus. So I referenced this the other day. Today, I should say, we're estimating areas with finite sums. Finite means a specific number, like 8 or 25 or 2. In a few days, we'll be talking about infinite sums. Okay. So the starting point for us in differential calculus, which is the first 4 months of school, is finding the slope of the tangent line. Right? That was a big starting point for us, and then it took us on this lovely path. As we start this second half of calculus, the starting point for this branch, integral calculus, is finding the area under a curve. And then we'll be talking about all of the things that we can do with that and what it means. While these two things seem very disconnected, they are so connected, and we'll connect these two concepts as we work through this chapter and we learn something called the fundamental theorem of calculus. I mean, how important does that sound, right? Okay, but for today, we're just estimating areas. So this is something we talked about last year. Suppose that an object travels with a constant velocity. Well, let's just draw a little picture here. So on the y-axis, I have velocity, and I just picked some units, meters per second. I don't know, maybe it goes up to like 15. I don't know, just picking numbers. On the x-axis, I have time. I don't know, maybe go 1, 2, 3, 4. Again, I'm just picking numbers. If an object travels with a constant velocity, that means the velocity is the same the whole time. My question here is, what does the area under the velocity curve represent? So two things. I want to answer that question, but I also want to review the phrase area under the curve. When we talked about area under the curve in pre-calculus last year, we really had to make sure we defined that well. Area under a curve, by definition, means between the curve and the x-axis. That's a really, really, really big deal. Okay, so now that we've made sure we clarify that phrase, let's take a look. Here's my curve. Here's my x-axis. Gosh, we love this, right? The area between the curve and the x-axis is a rectangle. I mean, this is just a geometry question, right? So the area equals base times height. The base is, based on my numbers I picked, the base is 4, and my height is 15. And so the area is 60. But the question didn't just say find the area under the curve. It says, what does the area under the curve represent? Let's talk about some units. The base is measured in time. I should have squeezed that in there, right? So that 4 is measured in seconds. That 15 is measured in meters per second. So when I multiply those units together, when I multiply those quantities together, what units do I end up with? And this is an open question for anyone. What are the units for my answer?
Meters.
Perfect, thank you. 60 meters, right? Because we had seconds, we multiplied that by meters per second, the seconds cancel, we're left with meters. I mean, gosh, even think about this when we go back to pre-calculus, or like middle school math, I should even say. We learned distance equals rate times time. So we did the rate, which is 15, times the time, which was 4. Doesn't it make sense we should end with meters? So the area under the velocity curve represents our distance traveled. Okay, and that's something that you did address last year in pre-calc, I believe. I say I believe because, you know, with us kind of skipping out of school in March, but I think Mr. Pack did this way before March. Okay. Great, easy, piece of cake, right? Area, rectangle, great. But what if our object does not travel with a constant velocity. I mean, right, we know things are not constant. So I don't know, let's just draw a graph. I'm going to just keep the same numbers. Not that it matters, we're not actually going to do the math here, but I don't know, what if it looks like this? And your graph does not have to match mine exactly, right? Just make sure it's not a horizontal line. The question here is, can we still find the distance traveled? Can we still find that area under the curve? Well, I mean, I specifically picked something that, you know, if I shade this in, I think a lot of us would look at that and say, no, we didn't learn anything about this shape in geometry. This is not a triangle. It's not a trapezoid. It's not a circle. This is an irregularly shaped figure. Right? So the question is, how do we find the area? Well, guess what? We did this last year, right? We estimated the area under the curve. We can estimate by using a bunch of rectangles. And as soon as we start doing this, it's going to come back to you, I promise. So we can estimate the area using what we call a Riemann sum. I'll come down there and define that. But we said we can estimate it by using a bunch of rectangles. And I'm going to put in parentheses because now we're going to start to use some more mature vocabulary. We're going to use a Riemann sum. And just in general, a Riemann sum is, well, let's see, it's a specific form of estimation. In which the region is divided into a finite, or I'm going to in parentheses say a given, finite or given number of so-called, let's call them strips. Okay. The reason I said it's a specific form of estimation, because, you know, we talk about estimating things and, you know, unless someone tells you exactly how to estimate, we could all come up with different numbers, right? So a Riemann sum is a very specific method, which means we're all going to get the same answer, okay? So I am going to pause here because I know I wrote a lot here. And so some folks might still be kind of catching up here. But what we're about to do, 2/3 of it you have done in the past, okay? In fact, I asked you to do it in your homework last night. Question number 10. Okay, I'm going to slide. You ready? We have the same picture 3 times. In fact, tomorrow or Monday, I'm sorry, we'll see it a 4th time. So we have 4 options here. So we're going to estimate or approximate the area under the curve, which again, remember means between the curve and the x-axis, using 4 subintervals. So this is that finite number. There's our equation, y equals 1 plus radical x. And they want us to look at the area between 0 and 2. Option number 1, and this is what I asked you to do in your homework last night, is what we call a left Riemann sum, or we could just say left rectangles, or we could just say a left sum or a left-sided sum, the key word being left. So the first thing we need to do is we need to take our interval. By the way, this is our A and this is our B. We're going from 0 to 2. And if we're going to divide it into 4 equal pieces, we need to figure out how big they are. Now, I know this one we don't need a formula for, but if you remember from last year, we had a formula to find the change in x. Delta x equals B minus A over N. And delta x is just the width of each rectangle. So delta x equals 2 minus 0, and then N is 4. Now, I know we didn't have to write this out to get that, right? You're going, oh, it's a length of 2 We're cutting into 4 pieces. I know we didn't need a formula for that, but I liked recalling this notation here. So that means we're going to go from 0 to 2. We're going to cut it into 4 equal pieces, and each one has a width of 1/2. So this is 0, 1/2, 1, 1.5. I'm going to call it 3/2, and 2. All right. I know I'm going to go through this a little slower, but then we'll speed up as we move on. So we're going to draw 4 rectangles. And if we're using a left Riemann sum, that means we're going to find the height on the left side. So my first rectangle, I'm using different colors, is going to sit between 0 and 1/2. I'm going to go to the left side. I'm going to go up until I hit that function, and that is the height of my first rectangle. The y value here comes from the function. My x coordinate was 0, so my y value here is 1. And we'll come back to that. All right, my next rectangle sits between 1/2 and 1. There's my base. I go to the left side. I go up, 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 up until I hit the curve. That's the height of my second rectangle. By the way, they're supposed to look like they're all the same size, but clearly mine don't. And by same size, I mean same width. The height here is this point. This x value is 1/2. So when I plug that x in, I get 1 plus the square root of 1/2. That's the height of my blue rectangle. I'm going to do my third rectangle. It sits between 1 and 3/2. I go to the left side. I go up, 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 up until I hit the curve. That's the height of my next rectangle. That point was where x equals 1. When I plug in a 1, I get a height of 2. And then my last one sits between 3/2 and 2. I go to the left. I go up, 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 up until I hit the curve. That's the height of my last rectangle, right? They said n equals 4. I only drew 4 rectangles. This point here corresponds to x equals 3/2. So the height, or the y value there, is 1 plus the square root of 3/2. Okay, we want to find that area. So it's just 4 rectangles. The first one has a base of 1/2 and a height of 1. The second rectangle also has a base of 1/2 and a height of 1 plus the square root of 1/2. My third rectangle has a base of 1/2 and a height of 2. And my last rectangle has a base of 1/2 and a height of 1 plus the square root of 3/2. That right there is an estimate for the area under the curve. Now, I could have saved myself a heck of a lot of time and space by saying, oh my gosh, they all have a base of 1/2. So let's pull that out in front. And I'm left with 1 plus 1 plus the square root of 1/2 plus 2 plus 1 plus the square root of 3/2. Right? Another way to write it. In fact, that'll just make it easier to type into a calculator. 1, 2, 3, 4, 5 plus the square root of 1/2 plus the square root of 3/2. And I'm doing this just for a reference point. We don't need the decimal. Okay, this is my answer, but my approximation as a decimal is 3.466. Okay. And I'm hoping by now you're going, oh yeah, I remember doing this last year. Okay. Please, if at any point you have questions, please just ask. All right, we're going to speed up a little bit. We've got 2 more options for estimating area. If option number 1 was using a left Riemann sum, guess what option number 2 is? Using a right Riemann sum, or a right rectangle. By the way, nothing else has changed. I'm still doing the same function. I'm still going from 0 to 2, which means my base values are still the same, and my rectangles are all going to sit in the same spot. So my first rectangle sits between 0 and 1/2, but this time I'm going to the right side, and I'm going to go up, 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 up until I hit the curve. And there's my first rectangle. Let's see, the height there is 1 plus the square root of 1/2. By the way, if at any point you're not sure where I'm getting any of these numbers from, please ask. Let's see, my second rectangle still sits between 1/2 and 1. I'm going to go up on the right side until I hit the curve. That's the height of my second rectangle. That height there is 2. My third rectangle, up, 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 up. Ooh, that wasn't a very good capper there. 1 plus the square root of 3/2. And then last one, between 3/2 and 2, I go to the right side. I go up, 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 up until I hit the curve. And there's my fourth rectangle. This point right here came from when x equals 2, so it's 1 plus radical 2. Again, I have 4 rectangles, base times height, base times height, base times height, base times height. Each rectangle has a base of 1/2. So instead of writing it 4 times, let's just multiply our final answer by 1/2. So my first height was 1 plus the square root of 1/2. My second height was 2. My third height was 1 plus the square root of 3/2. And my fourth height is 1 plus the square root of 2. And again, this is not necessarily something you need to type in. 1, 2, 3, 4, 5 plus. I'm just getting it for, again, a reference point. The square root of 1/2, the square root of 1.5. I could have typed these in before class started. That would have saved us some time. I got 4.173. So just as kind of like a quick little summary here, when I used a left endpoint, I was missing some area. So this would be an underestimate. I think we can all agree. When we switch to right rectangles, look, we've got all this extra area. This will be an overestimate. Great. What do we think option number 3 could be? Anyone want to take a stab at it?
Either averaging the two of them or middle.
I love it. Thanks, Matt. In fact, those are going to give us 2 different answers. So I love it. Matt said we could either average the 2 answers we just got, right? If this one's too small and this one's too big, let's just average them. Or Matt said, instead of using the left or the right, what if we use the middle? I love it. Let's do that one. We're going to do a midpoint Riemann sum. But you're absolutely right, Matt. We could also just take those 2 numbers and average them and maybe get a little bit closer. This is not going to be the same as averaging, and that's something we'll talk about next week. Okay. Midpoint Riemann sum does not change the fact that I'm still going to be using 4 rectangles. So my 4 rectangles still, we still have those same x values there. And I'm going to draw on my bases. My first base still sits between 0 and 1/2. My second base still sits between 1/2 and 1. My third base still, you get the idea. The bases aren't changing. The number of rectangles are not changing. The only thing that's changing is where I'm finding the height from. So instead of going on the left or on the right, we're going to go smack dab in the middle. So I'm going to go to the middle of my first rectangle. I'm not going to draw it in, but I'm going to go up, 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 up until I hit the curve. That's going to be the height. So I go a little bit to the left and a little bit to the right so that it lines up with my base. So the midpoint says we're going to go to the middle of the interval, which the middle of 0 and 1/2 is 1/4. We're going to go to x equals 1/4. We're going to go up until we hit the curve. That'll be the height. Let's go ahead and find the height, right? Remember, the function is y equals 1 plus the square root of x. So if I used x equals 1/4, this is 1 plus the square root of 1/4. That's the height of my red rectangle. Great. Next rectangle, mine's blue. I go to the middle. I go up, 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 up until I hit the curve. That's the height. So I go to the left half. I go to the right half. Halfway between 1/2 and 1 is 3/4. So my x value is 3/4. So my height here is 1 plus the square root of 3/4. I'm going to do my next one. I'm going to go to the middle, go up until I hit the curve, a little bit to the left, a little bit to the right. You can tell I'm speeding up a little bit. It's a lot of redundancies. Let's do a quick little 1/4, 3/4. If we're equally spaced, this should be 5/4, and this should be 7/4. So we're not changing how many rectangles we're using, but maybe the numbers aren't as friendly now. I mean, they're not horrible, right? But now we just have a lot more fractions we're dealing with. But still, the amount of work we're doing is really the same. So let's see, this will be a height of 1 plus the square root of 5/4. Excuse me. And then my last one, getting a little bit on the messy side, but that's okay. This height is 1 plus the square root of 7/4. What I like about this, okay, I said it was about the same amount of work, and it really is, but we first had to maybe, find some new x values. What I like about this option, though, is that we have a little bit of too much area, but then we have a little bit of, of area we're missing. So maybe those will help counterbalance each other a little bit. Okay, a little bit. Depending on the shape of your graph, it may not be that great. All right, so again, each rectangle still has a base of 1/2. And then the heights are 1 plus the square root of 1/4, 1 plus the square root of 3/4, 1 plus the square root of 5/4, 1 plus the square root of 7/4. Beautiful. And you know what? I am going to take the time to type that in. And I apologize. I should have just had it done earlier, but I've got 0.5 times. Let's see, I've got 1, 2, 3, 4 plus the square root of 0.25, the square root of 0.75, the square root of 1.25, the square root of 1.75. And I got 3.903. Which, I mean, makes sense to us. It is falling somewhere between our left and our right estimations. Okay. Whew. Tedious. But we didn't use any calculus, did we? There's no calculus in here. Gosh, it's just a bunch of geometry, isn't it? I think we like that, don't we? I haven't talked about a single antiderivative yet, have I? So we're taking a bit of a break from those. All right. Questions before we flip it over to the back? Okay. I know this is where I keep running short on time, isn't it? What time do we get out of here? 9:51. Okay, so let's just do this last question here. It says approximate the area under the curve. Here's our curve with a right Riemann sum using 6 subintervals. Now, on the last 3 pictures, I gave you a computer-generated graph. And so we felt like, okay, we have a good graph. We didn't actually use the graph at all. All we really needed was the function so that we can find the heights. I don't care what your graph, I don't want to say I don't care. It does not matter what your graph looks like. And that's kind of what I want to prove with this one here. We're going from -3 to 3. We want to cut that into 6 pieces. So let's see, delta x equals 3 minus -3 divided by 6, which is 1, right? We could have done that without writing anything down. So -3, -2, -1, 0, 1, 2, 3. Be very careful. We're dividing it into 6 pieces, but that gives us 1, 2, 3, 4, 5, 6, 7 x values. We're not going to use them all. Now, the point I'm trying to make here is you don't need a good graph, so you can draw any graph. I just, drew something that's doesn't really look like e to the x. But if I'm using a right Riemann sum, I'm not going to draw all 6 rectangles. My first rectangle sits between -3 and -2. I find the height from the -2. I don't need the graph to do that. I need the function. So the height of this rectangle is e to the -2. I'm going to draw one more rectangle. My next one sits here. I go up on the right. Again, not an accurate picture. This is an x value of -1, so the height here is e to the -1. I'm going to go all the way until I get the last one, and on the right side, I have that 3, so the height here is e to the 3rd. The base of each rectangle, delta x, is 1. So it's 1 times, I don't need to write that down, and then I just have my heights, e to the -2 plus e to the -1, e to the 0, e to the 1st, e to the 2nd, and e to the 3rd. I just skipped the ones in the middle because I knew what was going to happen. 1, 2, 3, 4, 5, 6 heights because they wanted 6 rectangles. We should always do that quick check at the end to make sure. Okay. All right. Hey, I know I'm out of time. That's why I said we needed 2 days.